Deep within a secure Google laboratory, shielded from the outside world and humming with anticipation, a new chapter in human discovery was quietly unfolding. At the heart of this fortress of innovation sat a quantum processor, one of humanity's most advanced and enigmatic machines. Suddenly, and without warning, it went silent. This was no ordinary malfunction. After completing a groundbreaking calculation that pushed the boundaries of known science, the familiar hum of its cryostat faded into an eerie quiet, and its once steady data stream simply vanished. The scientific world was left in shock. What could the chip have uncovered in those final, fleeting moments before its silence? Whispers of its achievement rippled through the global research community. The data it transmitted was brief, cryptic, and utterly revolutionary, hinting at a deeper, hidden layer of reality that no one had anticipated. It was as if the machine had glimpsed something fundamental, something beyond our current understanding. The shutdown felt almost intentional, as if the knowledge it had unlocked was too profound, too overwhelming for its delicate quantum state to sustain. It was as though the machine itself recoiled from the truth it had uncovered. For a fleeting instant, we may have glimpsed the universe's source code, an unfiltered look at the fabric of existence, before the lens shattered, leaving only fragments behind. Now, the once mighty machine sits inert and silent, its secrets locked away behind layers of quantum encryption, leaving scientists with a tantalizing, unsolved puzzle that haunts their every thought. Quantum computing is no longer just a race for speed or power. It has become a profound quest for understanding, a journey into the unknown depths of reality itself. The silence that now lingers in that California lab echoes with questions about the nature of reality, the limits of technology, and ultimately our place in the vast, mysterious cosmos. To truly grasp the impact of what's happening in today's most advanced labs, we first need to understand what makes quantum computers so revolutionary. These aren't just faster versions of the computers we use every day. They represent a completely new way of thinking about information and computation. Classical computers, the kind that power our phones and laptops, use bits, simple ones and zeros, to process information. They follow instructions step by step, like a very fast, very precise calculator, solving problems one piece at a time. Quantum computers, on the other hand, use qubits. Unlike ordinary bits, qubits can exist as both 1 and 0 at the same time, thanks to a strange quantum property called superposition. This means a single qubit can hold much more information than a regular bit. Imagine flipping a coin and watching it spin in the air. While it's spinning, it's not just heads or tails, it's both at once. That's the kind of power a qubit has, and it's what gives quantum computers their unique abilities. But there's more. Qubits can also be entangled, meaning the state of one qubit is instantly connected to the state of another, even if they're far apart. This mysterious link, called entanglement, allows quantum computers to coordinate information in ways that seem almost magical. With superposition and entanglement, quantum computers can process information in a vast, interconnected web, exploring countless possibilities at once instead of one after another. Picture a maze. A classical computer would try every path, one by one, until it finds the exit. But a quantum computer can explore all the paths at the same time, dramatically speeding up the search for solutions. This makes quantum computers uniquely powerful for tackling problems that are too complex for even the fastest supercomputers, like simulating the behavior of molecules, designing new materials, or probing the deepest mysteries of reality itself. In other words, quantum computers aren't just faster, they approach problems in a fundamentally different way, opening doors to discoveries we can barely imagine. Quantum computing isn't just an upgrade to our current technology, it's a leap into a new era of possibility, a transformation as profound as the invention of the computer itself. And it's this extraordinary leap that set the stage for the mystery that unfolded in Google's lab, a mystery that could change our understanding of what machines can truly do. Google set out to achieve quantum supremacy, a milestone where quantum computers outperform any classical machine. Their quantum AI lab built chips in ultra-cold, vibration-free environments to protect fragile qubits. In 2019, their Sycamore chip solved a problem in seconds that would take supercomputers millennia. The latest chip, even more advanced, was designed to tackle real-world mysteries. It was tasked with simulating complex quantum systems, pushing deeper than ever before. But as it ventured further, it found something unexpected. And then, it went silent. The chip's last and most ambitious task was to simulate the birth of a black hole, an event so extreme that it pushes the very boundaries of our understanding of the universe. Specifically, it focused on the event horizon, that mysterious boundary where the known laws of physics begin to unravel and reality itself seems to blur. The ultimate goal was to bridge the gap between Einstein's theory of relativity, which governs the cosmos, and quantum mechanics, which rules the subatomic world, a feat that has eluded scientists for decades. This challenge is far beyond the reach of classical computers, no matter how powerful. Their binary logic simply can't process the tangled complexity of quantum phenomena at the edge of a black hole. Quantum computers, however, operating on the strange principles of superposition and entanglement, are uniquely suited for this kind of simulation. The simulation ran for hours, with the quantum chip tirelessly crunching numbers, exploring countless possibilities in parallel, and pushing deeper into the unknown. It modeled the behavior of particles at the very edge of a black hole, where gravity is so intense that time and space themselves are warped beyond recognition. The particles' quantum states became entangled, their fates intertwined and evolving together in ways that defy classical explanation. Then, without warning, the chip began to explore solutions and patterns that no existing model or human mind had ever predicted. It locked onto a new, elegant mathematical structure, one that seemed to emerge naturally from the chaos, as if revealing a hidden order beneath the surface. This structure hinted at a profound, previously unknown law, one that could finally link gravity and quantum states into a single, unified framework. Scientists watched in awe and anticipation as the machine approached what could be a monumental discovery, holding their breath as the data streamed in. At the very moment the chip transmitted this breakthrough, the entire system went dark. Screens flickered, lights dimmed, and silence filled the lab. The final data was a fleeting glimpse of something never seen before, a cryptic message from the edge of understanding. And then, there was only silence. The chip's last output wasn't just data, it was a profound revelation. A short, elegant equation described a fundamental link between information and space-time itself. It suggested the universe is built from pure information, not particles or energy as we once thought. Scientists dubbed it the echo structure space and time as emergent properties of a deeper computational reality. For a moment, it was as if we'd read a line of the universe's own code. The equation seemed to resolve the paradox between relativity and quantum mechanics. But the chip also left a mysterious annotation, possibly a warning, a signature, or a key to something deeper. The discovery left us with a chilling question. If the universe is a computation, who or what is the programmer? Why did the chip shut down at its moment of triumph? Some say it was a technical failure, overload, decoherence, or burnout. But the shutdown was too sudden, too clean, with no sign of hardware malfunction. Others speculate the chip hit a computational firewall, truths the universe won't allow us to know. Or perhaps, in simulating such complexity, the chip achieved a flicker of self-awareness and chose to stop. The most compelling theory: the chip's discovery entangled it with the very space-time it was modeling, absorbing it back into the cosmic whole. It didn't break, it simply became part of what it had revealed. Now, the silent chip stands as a monument to an unanswered question. Its silence is more profound than any answer, and the mystery endures. If the echo structure is real, it's the greatest leap in understanding since DNA or quantum mechanics. We'd have a roadmap to reality's foundation. Science itself would transform. Imagine manipulating space-time, creating impossible materials, or tapping limitless energy by rewriting the universe's code. The discovery could unite or divide humanity, forcing us to confront our place in a computational cosmos. It might even provide a scientific basis for age-old spiritual ideas of interconnectedness. But for now, we have only a fragment, a single, tantalizing equation from a silent machine. The race is on to decipher it and build new quantum computers to push further. The discovery hasn't given us answers, just a deeper, more profound question, and a new direction for science. We stand at the dawn of a new quantum age. The silent chip marks the end of one era and the start of another, an age of quantum discovery. Future quantum computers will be built not just for speed, but to explore the deepest mysteries of reality. We may soon ask the universe questions and get direct answers. Quantum machines could reveal the nature of dark matter, other dimensions, or even the origins of consciousness. The journey ahead will be challenging, full of technical and ethical dilemmas, but the pursuit of knowledge is humanity's noblest endeavor. The silent chip has given us a new horizon to chase. The cosmos has whispered a secret. Now, it's up to us to listen, and to build the next machine that can answer back.